This video will give you an introduction of within subjects designs. Within subjects designs are designs where each participant is tested under multiple conditions. So each level of your independent variable, where your independent variable is what establishes the groups that are being compared when you're doing mean comparisons in ANOVA. But within subjects designs is that every single participant is in every single level of that independent variable. And this is what the equation looks like for this type of model. Very similar to the between subjects designs, but slightly different based on the variances that are being used. These within subjects designs are also called correlated error models, but the one that you would most likely hear is repeated measures designs, or this is can also sometimes be called longitudinal ANOVA. So this goes by several different names. But regardless of the name, the biggest point is that every participant is in every level of your independent variables. So each participant is in each group. So now your ANOVA is more like a paired sample t-test than an independent sample t-test. So for the between subjects designs, you have independent groups where the participants in each group are only in one group. Whereas with now the within subjects design, it's like a paired sample t-test where we use paired sample t-test for like a pre-test, post-test comparison. And this is where every participant is in both groups. It's both in the pretest and in the post-test. But now we have 3 or more of these groups to be able to do this within subjects designs ANOVA. And so the subjects are providing multiple values for the dependent variable. And so for each level of the independent variable, each participant will have a value for the dependent variable. So the means of the dependent variable are still what's being compared across the groups, just as in any other ANOVA design. But now you have each participant is at every level of the independent variable. And so this repetition can be over time, and most often we see it over time. So it's 3 or more time points where each participant has a value of the dependent variable at each of those time points, but it could also be over treatments where it's like a leveling or a stacking of treatments, or it could be something where it's the increase of sessions, so the number of sessions, but you are measuring the dependent variable at each session. So then session 1 dependent variable value could be compared to session 3 dependent value and look and see if there's mean differences across all these different treatment levels. So also from this balanced design, and because you're comparing each person to themselves just over the levels of the independent variable, you actually are increasing the power when you're using this repeated measures design, and it's increasing the consistency of your comparison that you're doing. And so this is actually a really good thing. You also are increasing the power because now with your sum of squares calculations and your mean squared calculations, the n value for each one of your groups is going to be, and your overall total sample size is going to be larger since each individual is counted as one for each level that they are part of. Now, because you don't have a within term now, this types of variance that are being used in the computation of these types of ANOVA models and how these sum of squares are being computed is a little bit different. And so we still have this between sum of squares, but now it's a little bit different in that your between sum of squares is looking at each level of the independent variable, but also each individual subject, because now you have each individual subject being compared to themselves at each level of the independent variable. And that's where this interaction is that comparison of each subject to themselves at each level. And so that's where you are looking at where are these differences between these different groups. So you have to take into consideration the differences between the levels as a whole, and then also the differences between each subject just within themselves, and then do this combination of level with subject. And so then this also impacts the degrees of freedom for between, where the degrees of freedom between are also dependent on the levels of the independent variable, the number of subjects that are included, and then also looking at how many of those subjects are also at each one of the levels. And so then when you start looking at the degrees of freedom, the degrees of freedom for A are really about the number of levels you have in your independent variable minus 1. Your degrees of freedom for your subjects is the number of subjects you have overall minus 1, and then the interaction between the two, just multiply these two degrees of freedom together. So here we're just looking at the drawn out equations that are used for computing each of these values. So remembering again that you have your sum of squares of your levels, your sum of squares for each one of your subjects, and then the sum of squares of each subject at each level. And so these are how you are calculating. The thing to make sure to pay attention to is that for all of these, we no longer have a group mean that's part of the calculation. All of these are using the grand mean to be compared. And the closest thing to a group mean would be this level mean. So for each one of the levels, it could be compared there, but then also you have your subject mean. So those are the closest thing to actual group means. But this is how you calculate the sum of squares for each one of these pieces and their degrees of freedom. And so then you do get similar to the between subjects designs, you get your 3 different mean squared values, and your F ratios are the same because your S, or your subject, is a random factor. So subject is considered to be random, and so your F ratios are calculated the same as between subjects designs. So while the calculation itself for the F ratio is similar, what is different for these within subject designs is this error term. And this error term a lot of times is it's a certain notation that's used. So this Dimitrov notation is typically what's used, and it's basically calculating the error as a residual term. And so this is looking at the residual for each one of the levels, taking into consideration the subjects. And so we can kind of see the parallel between this levels and subjects term is related to this residual or error term. But there's really no other way to calculate your error term, you have to use one of these special notations. The other thing about these within subjects models is that you do not get a main effect for your subjects, so each subject compared to themselves, and you do not get a term or a F ratio for this interaction of each subject at each level.